likely this lecture will be fairly short, on the order of 30 to 40 minutes or whatever, because we actually did a whole heck of a lot of groundwork for this topic last Friday. So let me mark the rule sheet and see and opt in. So an open loop op-amp circuit is one that looks something like this. So we have our op-amp. We're going to have some positive power supply voltage VCC plus, a negative power supply voltage VCC minus. Here's our output pin of our op-amp. We may or may not see some loading resistor connecting this guy to ground. Doesn't necessarily have to be there. We may or may not see some resistor, I'm going to call it R plus, connected to the non-inverting input terminal. We may or may not see some resistor, which I'm going to call R minus, connected to the inverting input terminal. But we are definitely going to have some input voltage, which I'll call V1, and some input voltage, which I'll call V2. So in an open loop op-amp circuit, we do not have a feedback loop that is connecting our output terminal to either of our input terminals, okay? So this is effectively identical to what we discussed at the end of the lecture on Friday. We have some differential voltage, which is simply the drop between the inverting input terminal voltage, excuse me, the non-inverting input terminal voltage V plus, minus the inverting input terminal voltage V minus. And it gets scaled by the gain of the amplifier and appears at the output. If the gain is larger, or excuse me, if the product of the gain and that differential voltage is larger than our power supply voltages, we have saturation. If it's not, we're operating in the linear region. The overwhelming majority of useful open loop op-amp circuits operate in the saturation region, okay? So let's look at a specific problem. Let's say that I have a positive power supply voltage of 10 volts, a negative power supply voltage of negative 10 volts, I'm going to apply an input voltage Vn that's going to vary here. We're going to figure out how this guy works. And then I'm going to apply what I'm going to call a reference voltage, V reference here. And for the sake of this particular example, let's say that our reference voltage is 2 volts with respect to ground. And here is my output voltage, okay? So what my goal is for us to create a plot where we have V out on the vertical axis and V in on the horizontal axis. And we want to let these guys range, or excuse me, we want V in to range from negative 5 volts to positive 5 volts. All right. So let's start with Vn at -5 volts. We're not going to fill out the whole thing here, but let's talk about what's happening, all right? So if Vn were -5 volts, what would our differential voltage be in this case? Yeah, -5 minus 2 is -7. Oh, it would help if I gave you guys some parameters. Let's say here that our open loop voltage gain is 1,000 volts per volt. Our input resistance is 1 mega ohm, and our output resistance is 1. So with a differential voltage of -7 volts, what would our output voltage be? Right, so -7,000. Is -7,000 volts more negative than VCC minus? Yes. So what is our true output signal going to be? -10, all right? So let's say that this guy right here represents -10. What's going to happen at, let's say, Vn is -2 volts. So what's Vd for -2 volts? -4, right? -2 minus 2 is -4. So what should our nominal output voltage be according to the gain of our system? Jared, you got any thoughts? -4,000. Okay, is -4,000 more negative than -10? Yes. So what is our real output of our system when Vn is equal to -2 volts? -10. So we're still in negative saturation, right? So here's -2. Just for the sake of argument, we can connect these 2 points because there's no reason anything should have changed anywhere between -5 and -2 volts, right? What's going to happen when Vn is equal to 0? What's our output voltage? So it'll still be at -10 volts, right? So this guy is going to continue on like so. At +1, what's going to happen? -1,000, which is still more negative than -10. So it's going to keep on trucking over here. At Vn is exactly equal to 2 volts. Our output should be 0. At Vn is equal to 3 volts, what's going to happen? It'll be +10 volts. And it's going to wind up staying positive for all voltages over here. So when Vn is, let's say, significantly less than our reference voltage, our output is pinned at negative saturation. When V out is significantly, or excuse me, when Vn is significantly greater than our reference voltage, our output is pinned at positive saturation. Any changes that we see are going to occur somewhere very close to our reference voltage, okay? Now, with a voltage gain of 1,000, what is our linear range for this system? So, right, it should be VCC minus divided by 1,000. What's that going to be? What's -10 divided by 1,000? -100. So we're going to see that this amplifier only linearly amplifies signals from negative 0.01 volts to positive 0.01 volts around that reference voltage. So practically, it's going to look like this. Okay. This slope isn't vertical, but it's really, really close. Okay. Incredibly close to being vertical. And the higher our voltage gain AV is, the more vertical that slope will be. So what this circuit is doing is comparing the input voltage Vin to the reference voltage Vout, and it is outputting VCC plus whenever Vn is greater than reference, and it is outputting VCC minus whenever Vn is less than reference. Okay, so let's write down that characteristic there. Vout is VCC minus for Vn less than Vref. Vout is VCC plus for Vn greater than Vref. And when Vn is really, really close to Vref, we do have a little bit of play to where we might have some linear amplification, but for the most part, we can practically ignore it because that linear range is so small. This guy is what's called a non-inverting comparator, because it compares a signal to a particular reference voltage. Any questions about the behavior of this guy? Everything seemed fairly straightforward. Ian?
Practically speaking, do you really get any limitations with what the reference would be? Does it have to be like within a certain range usually, or
It needs to be within your power supply voltages, but other than that, not really. We'll talk about how we can generate that reference voltage in a couple of minutes, because if you wanted to generate an off-the-shelf voltage of 2 volts, how could you go about doing that without buying a power supply or something like that, right? But before we do that, let's look at a slightly different circuit. We'll use the exact same power supply voltages, 10 volts and negative 10 volts. The change that we're going to make here is we are now going to apply our reference voltage to the non-inverting terminal. And for the sake of argument, let's just leave this guy as 2 volts. We'll apply our input voltage to our inverting terminal. And let's use the exact same parameters. AV is equal to 1000. Rn is 1 mega ohm. R out 1 ohm. All right. So let's walk our way through this thing in a very similar fashion. All right. Let's start with -5 volts for VN again. So if VN is -5 volts, somebody who isn't Ian, tell me what our differential voltage is going to be. Sarah, you have any thoughts? So so our differential voltage will be the voltage present at the non-inverting terminal, which is 2 volts, minus the voltage present at our inverting input terminal, which in this case is -5. So 2 minus -5 is +7, right? That's exactly correct. So we would see that when Vn is less than Vref, we're going to get very large positive voltages at the output, right? So for the specific case of -5 volts, this is going to look like +7,000 volts, which is much greater than VCC plus. And so it's going to look like VCC plus here, or 10 volts. And while I'm at it, I'll put this guy as -10. And skipping over a couple of steps, when we're at exactly, Vn is exactly equal to 1 volt, we would have 2 minus 1 is 1 for Vd, times our voltage gain of 1,000. That's out 1,000 volts is our output. Still much greater than VCC plus. At T is, excuse me, at T, Vn is equal to 0. Our output's going to be 0. And that's kind of our inflection point here. When Vn becomes larger than V reference, we're going to see that Vd becomes negative, which in turn means that we're going to have very large negative voltages. It's going to swing out this way. And oops. Because of the very small linear range, this transition is going to occur very rapidly. And as Cheston observed, we're going to get literally the exact opposite response as what we saw with our non-inverting comparator, right? So whenever Vn is less than Vref, we output high, or VCC plus. Whenever Vn is greater than Vref, we output VCC minus. Hold on just a second. Right. Not really. The naming convention for the inverting and non-inverting terminals really comes from the fact, well, it's not necessarily this case, but it's in general. A positive voltage applied to the positive or to the non-inverting input gives you a positive portion of your output. And a positive voltage applied to the inverting input terminal winds up giving you a negative portion of your output. So that's where it comes from. So it's not specific to this case, it's across all op amps. Yeah. Yeah. And it has something to do with feedback amplifiers as well, but in a way that's beyond the scope of this class. So like, when we talk about transistor amplifiers in 335 and 336, it'll probably be a little bit more clear, but we're not ready to discuss feedback loops and frequency dependent transfer functions and all that kind of stuff just yet. So this guy is obviously then an inverting comparator. And we can tell the difference between the two, even though they are extraordinarily similar, by where we apply our input signal. So if we apply the input at the non-inverting terminal, we have a non-inverting comparator. If we apply the input signal to the inverting terminal, we have an inverting comparator. All right, so how difficult was this? Hopefully not very. All right, so I want you guys to confer with each other. We're gonna design something now. Just using this very limited amount of knowledge, we are actually able to design a useful circuit. So what I want to have happen is I want us to make what's called an analog to digital converter. Okay. Or ADC, for which any input of 3.3 volts returns a digital high. That would mean V out is equal to 5 volt, and any input below 3.3 volts returns a digital low, or V out, is equal to 0 volts. So what would we need to do to make or realize this system? So let's start with a real basic choice. Is this going to be a comparator? Well, absolutely, because we're comparing our input signal to a reference voltage. So that's how we know whether or not we need to use a comparator circuit. All right. Now, do we want a non-inverting comparator or an inverting comparator? Caleb. Correct. We want a non-inverting comparator because when our input is above, we want the output to swing high. So that's why we want a non-inverting comparator. So I'm going to draw a circuit here. And because we want a non-inverting comparator, this is where I'm going to apply V in, and this is where I'm going to measure V out. Those are the only things that we've figured out thus far. All right. Mr. Bodie, what should our reference voltage be? Just 3.3, because that's what we're comparing things to. All right. Sunny, what should VCC plus be? Yeah, because we want our output when it goes high to hit 5 volts. So that tells us exactly what our VCC plus value needs to be. And Mr. Parrott, what should VCC minus be? I disagree.
Zero.
0, right. Because we want our output to hit 0 when our comparison isn't met, right? So we don't want it to hit -5, so that's why we don't use -5. So there's nothing remotely wrong with us using 2 different power supply levels. One of them just needs to be larger than the other. We're good to go. So this is what our simple analog to digital converter would look like. We have designed a useful circuit. Let's talk about how we might simulate it. So for those of you that brought a laptop, I'll give you a minute or two to pull it up and all that jazz. Brandon, what's up?
So obviously the higher you make the gain, the better it's gonna create a digital signal.
Mm-hmm.
Go faster. Is there like a limit where like it's not even worth making the gain any higher? Into the 6, you don't really need more, or
Yeah, so it's all so that's a very good question, and it all has to do with the linear range. So if the signals that you're expecting are going to be very, very close to your reference voltage, you want that gain to be really, really high so that you never spend a lot of time in the linear range. But if you're going to be dealing with kind of large scale signals that, you know, they're going to be 100 millivolts or more away from reference most of the time, you can work with a much wider linear range and you're still going to get the behavior that you expect out of it. Ian.
Could you, like, if you wanted some other way than just increasing the gain, like if you're limited to what character, could you also do like a voltage division so that your power supply voltage is lower, while it's still like outside of reference?
I'm sorry, I don't understand your question.
Like if the power supply that you're working with, like your overall everything, is like 5 volts. And
Okay.
you're doing a reference of 2 volts. Instead of just drawing from a power supply to the converter, could you give it a lower power to also decrease that linear range?
Okay, yeah, sure. So if you had a 5-volt supply and you wanted to make VCC something other than 5 volts, yeah, absolutely. You could use some sort of voltage divider circuit or something like that. The thing that you would have to worry about there are what the loading effects are going to be on your voltage divider circuit. And we'll talk a little bit about something kind of like that in just a minute with generating reference voltages as portions of VCC. So let me open a new schematic. The first thing that I'm going to put in here is my op amp. So I'm going to press the components button, and then I'm going to type in the letters U, N, I. Okay. So the only op amp I ever use in this particular class is the universal op amp. So I'm going to take it and notice right now that it has the inverting input terminal on top and the non-inverting input terminal on bottom. And then the power supply terminals have the opposite configuration. It doesn't particularly matter how all that stuff's lined up as long as we just connect things correctly. But what I'm going to do is I'm going to press Control. I thought that would do it. I was going to mirror it, and I thought that was Control M. Apparently it isn't. Control R to rotate it. And then I'm going to, let's see. Apparently it's been too long. Edit. Where is Where's the stupid button for mirroring? Mirroring was Control E. All right. Sorry, forgot my keyboard commands. So that's just putting the positive thing on top. It literally does not matter at all. All right, so I'm gonna have, let's see, 4 voltages in this circuit, right? VN, VREF, VCC plus, and VCC minus. To make my circuits less of a hot mess of wires and stuff all over the place, what I like to do is establish all my voltages kind of outside the working circuit. And so I'm gonna drop some voltages over here way on the left. So I press Control E to mirror it, and then I rotated it twice. So I'm going to take a voltage over here. I'm going to take another voltage, rotate it twice. I'm going to set it up like so. I'm going to put my 4th voltage over here, or excuse me, my 3rd voltage there, and then my 4th voltage here. And I know this looks like a bunch of garbage, but it'll make sense in a minute. I'm going to tie the negative polarity terminals of these 2 voltage sources together. And then I'm going to connect those, put that node as ground. And while I'm at it, I'm going to put ground as the reference for my other voltage sources. Now I'm going to do this label network name, and I'm going to put VCC plus as the label. And I'm going to put it here on the positive polarity terminal of voltage source V1. And then I'm also going to put that label on the power supply terminal of my op amp. And so what that does is it says whatever voltage I see here, apply here without having to run wires and stuff all over the place. So I'm making a simple DC, 2-channel DC power supply over on the left-hand side, and I'm just connecting that DC power supply to my op amp. And I can do the same thing with VCC minus. Put it here and here. I'm going to come back to my op amp real quick and just give myself some leads off of the op amp model to which I can apply my other voltages. So let's make the voltage for V1 5 volts. The voltage for V2 0 volts, because effectively we're just going to model the thing we just designed. I'm going to call V3 a reference voltage, which should be applied at my inverting input terminal. I'm going to call V4 my input voltage VN, which should be applied at my non-inverting input terminal. And now we need to establish these guys. So I'm going to set this guy to be 3.3 volts. And my input voltage, I'm going to allow to range from 0 to 5 volts. So let's talk about how we can do that. probably the easiest way to do it is to call it a sinusoidal input with an amplitude of 2.5 volts. So that means that it would swing from negative 2.5 up to 2.5. So it has a range of 5 volts. And then I introduce a 2.5 volt DC offset to bring it up to where it's now swinging from 0 to 5 back and forth. Is that, you guys understand what I'm trying to do there? Trying to make it go from 0 to 5. The frequency doesn't particularly matter, but since we are going to look at this guy as a function of time, I do need to put something in so that I know how long to put my time interval. So let's just do this as 1 cycle per second. So a frequency of 1 hertz.
Why didn't you just make the amplitude 5 and the DC offset?
So if I made the amplitude 5 with a DC offset of 0, it would swing from -5 to +5. Because whenever so the amplitude is the peak value measured from the horizontal axis, right? So it's going to go to the positive peak of 5 and then down to the negative peak of -5, back and forth, back and forth, back and forth. Setting it up like this means it's going to go from 2.5 to -2.5, and then I'm applying a DC shift to bring both the positive portion and the negative portion up by exactly 2.5 volts.
So V4 is the input voltage.
That's correct. V4 is the input voltage. And just for the sake of argument, I'm going to label my output node Vout as well. I know this looks like a whole heck of a lot of stuff, but at least there aren't wires crisscrossed all over the damn place. So the simulation that I'm going to run for this guy is a transient analysis. Transient analysis simulations are used to give me a time domain output, meaning a waveform as a function of time inherently, okay? So since I know that this guy is going to experience 1 cycle every second, I'm going to let it run for 3 cycles, which means I'm going to stop it at roughly 3 seconds. So I'm just going to put 3 in there and then leave everything else blank and press OK. And I'm just going to drop this over here somewhere on the circuit. Doesn't particularly matter where. Press this little running man icon. Oh, actually, let me do something real quick. It's not going to matter particularly for this circuit, but I do want to show you something. If we right click in the middle of the universal op amp, and this is the reason that I use the universal op amp, right here where it says spice model and then level 0.2, there are actually 4 levels that we can use, okay? Level 1 treats it as an ideal op amp, meaning that it does not care what the power supply voltages or anything like that are. It just does what it's supposed to do. Level 2 is an ideal op amp, but the power supply voltages matter. So it will give us the saturation distortion and all that kind of stuff that we are expecting to see. Level 3 adds in these quantities for where it says value 2. AVOL is the open loop gain. So we could change that right now. It's set to 1 meg or 1 times 10 to the 6, so 1,000,000. We could change it to 1,000 or 100,000 or whatever we wanted to just by typing it in there. GBW is what's called the gain bandwidth product. That is going to be very, very important once we start looking at frequency dependence of amplifier circuits. But for a DC circuit, it means absolutely nothing. And the slew rate is a representation of how fast the output of the op amp can change due to a change in the input signal. So for DC circuits, it means nothing. For AC circuits, it's just another type of distortion that we have to worry about. So for the purposes of this example, we can leave this guy at level 2 and be perfectly okay. But I just wanted to show you that so that you can really tinker around and use these parameters to model any practical op amp you want just by pulling stuff off the data sheet and entering it in here. All right, so I run my simulation, and what I get as a blank plot because I haven't told it what I wanted plotted on there. Now, a lot of you guys probably have a blank black screen up here. And if you're going to be printing things out, like physically printing things out, that's just going to waste tons and tons and tons of ink. So before we actually show you how to plot the waveforms, if you go into Tools and you click Color Preferences, and then you click this tab that says Waveforms, you can just click on the graph which parts you want to change. So I moused over the background and it said, click to change background color. Well, my background color is set to 255, 255, 255, which is white. I bet you guys is set to 000, which is black. So you could change it. You could do a red background if you really wanted to, or any weird hippy dippy color that you feel like. You can also click on these axis lines and change them from, you know, white to gray to black to all that kind of good stuff. So you can change literally all of your color preferences for your waveforms in here. Here it says V1 all the way through V12. So these are the default colors that it's going to use for every different type of waveform that you put on your circuit. So the first one is going to be 1. The second one you put in is going to be 2, and I have it set to go from green, blue, red, I don't know, teal, pinkish, whatever. Usually not going to be more than 2 or 3. So anywho, that's how you change all your colors and all that kind of good stuff. You can also change things on your schematic, like change the font size, change the thickness of the lines for your wires and all that kind of good stuff as well. But we're not going to spend 3 weeks going over all that stuff. And if you ever screw things up and don't like it, you can always just press the default button to go back to what it originally was. All right, so in how to put stuff in my plot is to just mouse over things in my schematic. So this symbol right here is for a voltage probe. So if I click on a node, I'm going to get a voltage. So let's click on VN, and we'll see that I have an output voltage that's sinusoidally oscillating from positive 5 volts down to 0 and back over and over and over again. And on that same graph, I can plot my output voltage. And so I can see that at what looks to be something around 3.3 volts, anytime my input is higher than that, my output goes high. And anytime my input signal becomes less than that, my output goes low. If I wanted to, I could right click on my graph and add a trace, and just add a trace that is 3.3 volts. And so that lets me put my reference voltage specifically, or I could have just moused over VREF and put a voltage probe there and all that kind of stuff. So we can see that absolutely 3.3 volts is the transition point between when my output voltage goes high and goes low, depending on what my input signal is doing. Now, this plot is a function of time. And while that can be useful, it's not necessarily the best way to represent what's going on with this circuit. So what I can do, I'm going to delete this 3.3 volt reference, and I'm going to delete this input voltage so that I only have my output showing. I'm going to mouse over the horizontal axis and right click. And I can change the quantity that I'm plotting against. So in this case, I'm plotting against time. But let's change it to the voltage seen at the node Vn. This looks exactly like the graphs that we were generating earlier. So I can see that this 3.3 volt reference is the transition point for my circuit. So anytime Vn is greater than 3.3, I output high. Anytime Vn is less than 3.3, I output low. So this is how you get a V out versus Vn graph. You just change the value of your horizontal axis from time to the quantity that you're trying to measure against.
How did you change that?
I moused over the horizontal axis. So I have this ruler icon now when I'm over that. And I right click. And then I just changed quantity plotted from time to the voltage V, open parentheses, Vn, which is just telling me I want the voltage present at this node, the positive polarity terminal of the voltage source that's generating my input voltage. You gotta learn how to speak LT spice. Brandon.
Since we're modeling Vn as like a sinusoid, are we actually just comparing to expected values? That we get to 3.3 so high or low?
We're not using the effective value at all. We were using the instantaneous value of it. Yeah. Any other question on this plot or anything? All right. So if I asked you guys to do something like this for your homework, including generating one of these V out versus Vn plots, you should be able to do it. Okay. If not, the video for this should be, and all of the previous classes should be up tomorrow morning so that you can refer back to them and all that kind of good stuff. All right, so let's circle back around to normal lecture prep. How could I edit this simple circuit to where I wouldn't need an external source to give me this voltage of 3.3 volts? Ian kind of accidentally brought it up a little while ago. I can use a simple voltage divider circuit where I can just establish a ratio of voltages to make this guy, that voltage at that particular node, 3.3 volts. So let me erase this guy right here. And I'm going to erase this guy right here and just tie this whole upper rail to a voltage of VCC is equal to 5 volts. Then I'm going to put 2 resistors in. One will be between VCC plus and my reference terminal, which is my inverting input terminal. And the other one will be between that terminal and ground in this case. But really it would be between this terminal and VCC minus if I had a dual supply setup instead of grounding one. Okay. So what's the ratio of resistors that's going to give me 3.3 volts at this node? Because this is a voltage divider circuit, that's really all I need to do is just control that ratio, right? I want the voltage drop over this resistor on bottom to be 3.3 volts, and I know that the total voltage drop over both of the resistors is 5.
As long as the bottom resistor is 3.3 total size of the summer.
Call this guy R1, this guy R2. Yeah. So that says 3.3 times R1 plus R2 is equal to 5 R2. So effectively, isn't 3.3 volts 2/3 of 5? I think, or 3.333 would be 2/3, pretty close enough for me, right? So we could make this guy 2 something and this guy 1 something.
I'm not sure I understand.
Shut up, watch. So the something, the units here are actually pretty important though, all right? And the reason why that is because our op amp does have an internal resistance that is not infinite that we need to worry about. So generally speaking, the resistors that we would use to form this biasing network need to be significantly lower in scale than the internal resistance of, or lower in scale than the input resistance of the op amp. And if we had a biasing network on the other side, they would need to be larger than the output resistance. So generally speaking, a kilo ohm size resistor is kind of the sweet spot because that's about 1,000 times smaller than the input resistance, which is usually on the order of mega ohms, and about 1,000 times larger than the output resistance, which is usually on the order of single ohms. So if we made this 1 kilo ohm resistor and a 2 kilo ohm resistor, we should see that gives us the proper ratio to make that voltage. It won't be exactly 3.3 volts, but it'll be close enough. If we wanted to get real finicky, we could use, I don't know, a 3.3 kilo ohm resistor and a 1.7 kilo ohm resistor and literally just make them add up to 5. And that's a lazy way to do it as well. So we can establish our bias voltages, or our reference voltages, by using a simple resistor biasing network so that we don't need an actual extra power supply to set this guy up. But it only works if we choose resistor values that are not of the same scale as the internal resistances of our op amp. All right, that's enough out of me for today, unless you guys have another question. On Wednesday, we are going to talk about positive feedback op amp circuits. And we're going to start that discussion with a small problem with our comparator design that I'll introduce on Wednesday morning.